Our next speaker of our conference is Manami Niijima.
Thank you for the introduction and thank you for giving me this opportunity. Today, I'm going to talk about something related to the construction of roots of real cubic by using origami. Origami from ori means holding and kami means paper. It's a Japanese art of paper holding, having a vast connection to pure mathematics, education, engineering, and more. There are several famous programs of geometric construction from ancient Greece, such as the doubling of the cube or the angle trisection. In turn out of after Garrard's error that we cannot draw them only by ruler and compass. For instance, we cannot construct cubic root of 2 only by ruler and compass. But we can construct cubic root of 2 by using origami paper holding. I will explain an explicit algorithm for this construction soon. Then my main theme will appear there. Here is the outline of my presentation. My presentation is divided into 3 parts. First, I will talk about the history and background. I will explain the axioms of origami with emphasis on axiom 6, which will play an important role in constructing the roots of real cubics. Next, I will define Beloch's curve, which appear from the construction of roots and explain our main result. Finally, we will briefly explain the proof of our result. Similarly to axioms Euclidean geometry, we have axioms of origami. The axioms of origami were arranged around the 1990s by Justin, Fujita, and others. The origami solution of real cubics is mainly due to Beloch in the early 20th century. We refer to Nedelenko for further details. I cited this table from Justin's paper. This exhibits 7 axioms of origami. And these are translations of the axioms into natural language. Our focus will be on axiom 6. Axiom 6 follows the following operation, giving 2 points P1 and P2 and 2 lines L1 and L2. There is a holding that place P1 onto L1 and P2 onto L2. We remarked that we cannot construct this hold only by ruler and compass. This axiom enables construction in the program from ancient Greece. I explain how to solve equation by using an origami. Now we explain Beloch's algorithm solving a real cubic equation by origami. This page is very important. because if you don't understand this page, you cannot understand my main result. Theorem. Suppose that segment of length ABC are given. ABC. Then we can draw A minus 1, 0, point P, B, A plus C, and line x equal 1 and y equal A minus C on the fixed xy plane on the origami. If we make a hold that places point A onto line x equal 1 and point P onto line y equal A minus C. A x equal 1, P y equal A minus C. Then the y intercept R of the hold line R. L is the solution of this equation. We can find every real root in this way. To find deeper inside there, we are interested in Beloch's curve f of a given real cubic equation defined as follows. We set point P, PQ equal P, B, A plus C. Definition. Suppose that A prime runs through x equal 1. Consider the hold line L that maps point A onto A prime. Point A onto A prime. The conditions 1 in theorem. Let P prime denote the image of point P by this L. Then the set of P prime and P form an algebraic curve, which we call Beloch's curve f. This curve is Beloch's curve f. I explain main theorem. Let fx equal 0 be Beloch's curve f of a given real cubic equation. We set P, PQ equal P, B, A plus C. Then the point P is its uniquely existing singular point of f, and the sign of the Hessian at P determines the shape of f. More precisely, consider the parabola G. Then we have following the equivalence. My theorem asserts that the situation depends on the relationship between P and parabola G. For example, in the left graph, P is on the right side of parabola G, and P is isolated point of the curve F. In the case of middle figure, P is the cusp of F. In the case of right figure, P is the intersection point of F. Do you have any questions so far? Okay.
No, it's clear.
Thank you. Okay, let's go. If we regard f as the intersection of the surface x equal fx and x equal 0, then we may capture the situation in a three-dimensional view. These three figures correspond to the solutions of those in the previous pages, respectively. In the rest of this talk, I will explain the proof of the main theorems. First, a direct calculation shows that P is uniquely existing singular point of F. Next, we study the trajectory of P prime when A prime runs through x1, x equal 1. Proposition 2.2 supports the P is fixed. Then for a hold satisfying the condition 1 in the theorem, and point A prime and P prime determined by L, the following are equivalent. 1. Point P and point P prime coincide. 2. The hold L passes through P. 3. AP equal A prime P holds. 4. The point of A prime is on the circle C with its center at P and its radius at AP. Since P prime is a reflection of P in L, P is on L if and only if P equals P prime. Since L is the perpendicular bisector of A prime, P is on L if and only if AP equals A prime P. Finally, the equivalence between 3 and 4 is previous by the definition of the circle C. Proposition 2.3. The number of intersection points of x equal 1 and the circle C is determined by the relationship between point P and the parabola G as follows. Note that G is determined by the focus point A minus 1, 0, and the directory x equal 1. If x equal 1 and C has two intersection points, then the distance between the line x equal 1 and the center P is less than the radius AP. So we have this equation. This implies that P is on the right of G. Other cases may be treated similarly. Then we obtain the following conclusion by combining proportion 2.2 and 2.3. Proposition 2.4, the orbit of P prime admits the following equivalence. Indeed, we have the following argument. Proposition 2.5, the shape of F at P is determined by the place of P as follows. For P plus Q squared is less than 0, if and only if P is an isolated point of F, this term equals 0 If and only if P is a cusp of P, this time is greater than 0. If and only if P is a self-intersection point of F. By proposition 2.1, P is a single point of fxy equals 0. The Hessian of fx at P is given by the following. By elementary calculus for two variable functions, z equals fxy takes local maximum minimum value at point P if Hessian is greater than 0, this figure, while it takes saddle point at point P if Hessian is less than 0. Since F is the intersection of z equals fxy and z equals 0, the condition 4p plus q squared is less than 0 implies that P is an isolated point, while this term is greater than 0 implies that P is a self-intersection point. Hold this term equals 0 and notice that P prime ST satisfied P is less than or equal to S by the relationship between AP and A prime P prime. By those facts that the orbit of P prime ST is connected, P is less than or equal to S, and P is a single point of F. We see that P is cusp of F. Here is reference. Thank you for listening my presentation.
Oh, thank you very much. Thank you. Let us thank the speaker. Thank you very much.